We're going to actually be doing like a little conceptual review on stuff before we get going with the actual FRQ. So this is going to be over circular motion and like really brief overview of some of the concepts with it. Okay, so with circular motion. So for example, this right here, this is a disk. This is what we would call its axis of rotation, right? This black line that's going through it, and then you can tell what direction it's going by this little arrow that's drawn right there. This thing would be rotating. So we could describe it as rotational motion, or in our case, we're going to be talking about circular motion. If we do more of like a bird's eye view, so we look down on it, say a circle like that, right? And this thing is going, let me make this a little more bold. All right, we're going in a circular fashion counterclockwise like that, okay? The thing is, if we're talking about vectors, you would want to be able to choose, my tip of my pen is just dying. You would want to be able to choose any point on this thing. Let's make that a bigger line. And like, let's say this blue point at the very top, right? If this thing is going counterclockwise, that means right there at that spot, the velocity, what we call the tangential velocity, is going to the left. Okay, and it's always tangent to the path, so like it's skipping right off the path, and it's always going to be a straight line. Okay, so tangential velocity. And then the acceleration, because remember, this is a motion type problem. We're always going to have displacement, velocity, acceleration, and all of their scalar quantities as well. So right there, it's velocity going straight to the left. Acceleration. Let's get a fancy color should we use for acceleration. Let's go purple. Okay, the acceleration would be pointing down towards the center of the circle, right? If the velocity is going to the left, this is my left, whatever it is for you. Okay, if the velocity is going this way, the only way it's going to turn is if the acceleration, right, is perpendicular to it. So the velocity and acceleration for circular motion will always be perpendicular to each other. And the acceleration, no matter where we put it, right, if we put it down here, then that velocity would still be a straight line tangent to the path right there, and the acceleration would be still pointing towards the center of the circle, the center of the circular motion, right? So those two things always have to happen. Okay, so that's like our talk about vectors. With the other thing that happens with circular motion, to describe it, is we have things like period and calculating speed and stuff like that. So if I am being asked about the period of something, first of all, period for circular motion is represented with a capital T. Capital T, for whatever reason, is the variable we use to represent period, and it's going to be in seconds, right? That's going to be like the standard unit of measurement for that. And there's two ways we can talk about this. If we were looking at this disk that's spinning around, let me erase some of this stuff. Right? Because it's a time and it's measured in seconds, if we were talking about what a period is, it's the time for one full revolution to happen. So if we have this object and it starts right here at this blue dot, by the time it goes all the way around this circle and is right back to where it started, that would be one period. And however long that entire circle took, that would be the quantity that we give the period. Okay? So that's one way you can find period. If you have like a physical thing, it's just how long it takes for one revolution. So we call that would be the time for one single cycle, with a cycle being just our general term for like a revolution. Okay. If you have a graph is the other way you can see this. Think about any trig function like sine, cosine. That's how we're going to represent Okay, for us to find the period when all we have is a graph, all you're going to do is you need to pick some point on the graph, and however long it takes for that graph to return back to its original position is what we would say the period is. So this horizontal axis right here, this is generally the time. And you always want to check what the units are, but it's usually measured in seconds. Okay, so let's say if I'm starting right here at 0, I'm starting at 0 and it's going up at the start. I need to trace along my graph and find when it gets back to at 0 going up. So if I start at 0 right here and it goes up, here it's at 0 but it's going down, so we're not back to the beginning. So and right there. Okay, so from this point at 0 to this point at 0, however many seconds that took, that would be the period. Okay, so there's, like we just went over, there's two ways to get the period of circular motion. There's actually just seeing how long it takes for one revolution, or there's looking at a graphical type of analysis and finding the period, how long it takes on that graph for one full cycle. Okay, let's see other things with circular motion. Circular motion is usually referred to as uniform circular motion. Okay, and these give us some really important things. Uniform being that is a constant speed. So if something is being described as uniform circular motion, we know that that's a given. Speed that it's rotating at has to be constant. Okay, the other thing is that the always. Okay, so those two rules are always there whenever we're talking about uniform circular motion. First one being that the speed is constant. Second one being that the net force has to always point towards 0, or the center. And remember, that makes sense because when we were talking about our vector stuff earlier, we were saying that the centripetal, the circular acceleration, is always going towards the center. And remember, whichever way the net force points, that's always going to be the direction that the centripetal or the acceleration points. Okay, so yeah, those two kind of go together, which brings us to the next part. Because this is motion, and we can always describe motion by the forces that are acting upon it, if there are forces involved with circular motion, then that means we can definitely use Newton's second law to describe what is going on. Okay, so circular motion problems will almost always ask you something about the forces involved. So just like any old Newton's second law problem, we have Newton's second law, which is the net force. Let me get my pen. Net force is equal to mass times acceleration. Okay, and when we have that, the only little thing that's going to change when we're talking about circular motion, this acceleration term right here, sometimes you'll see this with a little subscript C on it. That C stands for centripetal, which tells us that the acceleration is pointing towards the center of the circle. Centripetal literally means center, pedal seeking, so center seeking acceleration. Okay, we can substitute a different value in for this, a different expression, when we are evaluating any type of circular motion problem, depending on what we have. Like if you know what the acceleration is, you're good. You can just use Newton's second law as it is. If we don't know, what we can do is still look at the net force involved, and that is equal to mass of whatever object you're analyzing. And then the equivalent expression for centripetal acceleration right here is the tangential speed or velocity squared divided by the radius of the circular motion. Okay, so that right there is linear speed. That's that green arrow that we were drawing earlier when we were going over what the vectors are. It's the linear speed of your object, and that right there is the radius of the circular motion. All right? So that is the only thing that changes between like a standard linear Newton's second law of forces type of problem or a circular motion problem, right? It's just that we put in this different expression here for the centripetal acceleration. Net force, you still just add up all the forces that are acting on your object, put them right there for the net force. Nothing changes with that. Okay, mass, still just the mass of the object. All right? So like I said, brief overview, but hopefully this kind of refreshes stuff in your mind, helps you set some things up, and I will talk to you guys later.